Hello, everyone. In this lesson, we will learn how to implement the task of controlling a motor to alternate between forward and reverse operation using the S7-1200 PLC. In modern industrial applications, the level of automation in equipment is increasing, such as robotic arms on automated production lines and the opening and closing of automatic doors. Motors need to alternately rotate forward and backward to achieve specific functions. For example, a robotic arm may descend to grab materials, ascend to transport them to a designated location, and then retract to continue grabbing materials, repeating this cycle continuously. This alternating control of forward and reverse motion significantly enhances production efficiency and flexibility, as well as the overall automation level of equipment. So, how do we use a PLC to control a motor's alternating forward and reverse operation? Next, let's learn the task of this lesson. Implementation of alternating forward and reverse motor control using S7-1200 PLC. Let's first look at the specific task requirements. When the start button is pressed, the motor will first rotate forward for 3 seconds, then stop for 2 seconds. It will then rotate in reverse for 3 seconds and stop for 2 seconds, completing one cycle. This process will repeat for a total of 3 cycles before the motor automatically stops. During motor operation, if the stop button is pressed or an overload occurs, the motor will halt. Now, let's implement the task. We will determine the I/O address assignment table based on the alternating forward and reverse control requirements. The start button corresponds to I0.0, the stop button corresponds to I0.1, the overload protection corresponds to I0.2, the motor forward contactor corresponds to Q0.0, and the motor reverse contactor corresponds to Q0.1. Figure 7.3.1 shows the PLC peripheral interface wiring diagram. In the diagram, the control system has 3 input signals, SB1, SB2, FR, that can be directly connected to the PLC. However, since the PLC cannot directly drive AC loads, 2 output signals first drive low-power intermediate relay coils, KA, and then use the relay contacts to drive the AC contactor coils. The AC contactors KM1 and KM2 are interlocked to prevent short-circuit incidents. After completing the necessary peripheral wiring, we will design and write the control ladder diagram based on the control requirements and the I/O assignment table as follows. Program segment 1 controls the forward operation of the motor. When I0.0 or M2.5 is activated, the motor rotates forward and self-locks to maintain operation while starting timer T1. After 3 seconds, the M2.0 coil is activated, opening its normally closed contact to stop the forward motion of the motor. If the stop button is pressed or an overload occurs during operation, the motor will stop. After the motor has completed 3 cycles of alternating forward and reverse, it will automatically stop. It is crucial to ensure that the forward and reverse operations are interlocked to avoid short-circuit incidents. Program segment 2 controls the 2-second stop after the forward operation. When M2.0 is activated, the M2.1 coil is energized and self-locks, indicating that the motor is stopped after forward operation while starting timer T2. After 2 seconds, the M2.2 coil is activated, opening the normally closed contact M2.1 to complete the control for stopping the motor for 2 seconds after the forward operation, at which point the motor begins to reverse. Program segment 3 controls the reverse operation of the motor. When M2.2 is activated, the motor rotates in reverse and self-locks to maintain operation while starting timer T3. After 3 seconds, the M2.3 coil is activated, opening the normally closed contact Q0.1 to stop the reverse motion. If the stop button is pressed or an overload occurs, the motor will stop. It is important to note that there should be interlocking between the forward and reverse operations to prevent short-circuit incidents. Program segment 4 controls the 2-second stop after the reverse operation. When M2.3 is activated, the M2.4 coil is energized and self-locks, indicating that the motor is stopped after reverse operation while starting timer T4. After 2 seconds, The M2.5 coil is activated, opening the normally closed contact M2.4 to complete the control for stopping the motor for 2 seconds after the reverse operation, after which the motor will rotate forward again, completing 1 cycle of alternating forward and reverse operation. Program segment 5 counts the cycles of alternating forward and reverse motion. When the motor completes 1 cycle, the counter increments by 1. When the current value of the counter equals the set value of 3, it indicates that the motor has completed 3 cycles of alternating forward and reverse operation. The counter outputs M2.6, which energizes the coil and opens its normally closed contact to halt the control circuit, causing the motor to stop automatically and resetting the counter. We will use the Totally Integrated Automation (TIA) portal to create the project, program, and perform online debugging. You should create the project, define PLC variables, and complete the programming and downloading processes on your own. Once the program has been downloaded, we will proceed to debug and monitor its operation. Start the CPU. Enable monitoring. And open the simulator. Press the start button. The motor will rotate forward for 3 seconds, stop for 2 seconds, then reverse for 3 seconds, stop for 2 seconds, increment the counter by 1, and complete 1 cycle of alternating forward and reverse operation. After 3 cycles, the counter will output. The motor will stop automatically, and the counter will reset to 0. Let's check the status of the simulator. Press the start button. The motor will first rotate forward for 3 seconds, stop for 2 seconds, then it will rotate in reverse for 3 seconds, stop for 2 seconds, incrementing the counter. The current value, CV, will be 1, completing 1 cycle. When the motor continues this for 3 cycles, the current counter value will be 3. The counter will output, the motor will stop automatically, and the counter will reset to 0. This concludes our monitoring and debugging process for the alternating forward and reverse control of the motor. In this lesson, we primarily focused on implementing the task of controlling the motor's alternating forward and reverse motion using PLC counter and timer instructions. After class, I encourage you to try designing simpler programs to meet the control requirements. That concludes this lesson. See you next time.